So, hi and welcome to both our 17th lecture in the class Convex Analysis here at TU Braunschweig and the first lecture in the course Convex Optimization at Ames and AMI in Senegal and Rwanda. Okay, so topic of today is classes of optimization problems, and so it's the first of 6 lectures, which kind of form a group of lectures with the goal of developing a theory that allows us to both say to say how hard a certain continuous optimization problem is. So maybe I'm first writing down the headline. So the first lecture here is called Classes of Optimization Problems. So, and as always, in case you can't read something, or anything could be better with respect to tone, so the sound or video, please let me know so that I can try to improve. And of course, you could always interrupt me via chat and ask questions on what has been done here. Okay, so as I said, the question we're going to pursue here is the question: how hard is it to solve a problem? So the question in and of itself, how hard it is to solve a single problem, doesn't make that much sense, because you could always say, well, for this single problem, there's always the best algorithm which just outputs the solution. So that doesn't make much sense. So you could solve basically any problem with a really adapted algorithm which kind of just knows the solution in advance. So the question has to be posed a little bit differently. So what can be done? It can be done that we say we consider not a single problem but a class of problem, and want to have an algorithm which can solve every problem in this class. So one example, which is probably, I don't know if you, depending on your background, you may know linear programming. This is the minimization of linear functions over linear constraints. And linear constraints can be linear equalities or inequality constraints. So that's one class of function of problems. And so then you can try to come up with a method such that you give the method the data of the problem, which is the objective, and the data encoding the constraints. And with this input data given, it performs some operations and outputs the solution, or some solution, because solutions may not be unique. And then you can ask yourself, so how long would this take in the worst case? So how long? So what's the guarantee that I can? So what's the value or an amount of time and in which I'm really certain that I'm going to have a solution of a certain quality? That's a question that makes sense. And so what makes sense about this question is we have pinned down what is the problem, what have we used to describe our problem class, and what is our algorithm kind of allowed to use. So of course, if we allow to use basically all the information of the problem, which means the full objective function kind of, so every function value at every point, then minimization is trivial because you just pick the point with the lowest function value. So we need to be a little bit more careful. So and the things we're going to pin down here to describe what an optimization, the class optimization problem is. How do we describe a problem? What is the properties we're going to fix about the problem? What information is our algorithm allowed to use? And third, what is an approximate solution? Because for continuous optimization problems, it's basically hopeless to come up with an exact solution. It's always an approximate one, and so you need to find a notion of approximality. And so before we come to the class of convex problems, where the things are, at least for me, most interesting, let's do as a motivation and also as an example what these notions really say, a different example, which is global optimization of Lipschitz continuous functions on bounded domains. So that's our first example. So global optimization meaning we want to find the absolute minimum value which the function can assume of Lipschitz continuous functions on bounded domains. So that's our first example. So our problem class is then we consider as bounded domain a fixed one, namely the unit cube. And if the domain is bounded of our objective, we could always kind of scale and shift it around such that it lies within the d-dimensional unit cube. So with this I mean vectors with n entries, and each entry is between 0 and 1. And the objective function is a function which takes values from the unit cube and puts out real numbers. And this should be Lipschitz continuous. With constant L. So we assume that this L is also known to us. Also, one more thing is with respect WRT, with respect to the infinity norm. So probably I should say what this means. That would mean that if we have two values x and y and plug them into f, then the distance between these are just real numbers, is bounded from above by L times the distance of x and y in the infinity norm, which is the largest difference between two components here. And then the problem is minimize or find the minimum of f of x over x and q. And in this we would be both interested in some x which achieves the minimum and also in the minimum value. These are sometimes different objectives of the objective of the minimization. Sometimes you would just like to know. Yeah, zooming in a little. Let's try. I could probably just try it like that. Maybe this is already enough. This is always a trade-off between. Okay. So I hope this is better now. In case, maybe let's just try it like this. I will also try to write it a little bit larger. But this is then specific. I can always try to show it a little bit larger. So these are our assumptions. On the bounded domain, a Lipschitz continuous function with a known constant, and in this sense, but this doesn't make too much of a difference. It's just to simplify analysis. And probably the reason why we need Lipschitz continuous and not just merely continuous is the following. We would like to bound quantity like this. If we have some kth iterate, which our algorithm has constructed, we would like to bound this quantity here somehow. So if you have this, how far is this still away? You'd like to know something like this. But if our function is only continuous, it can kind of may vary as fast as it could like, right? If this is here now the unit interval, and we have a function which has a value here, it may, and we just know that this is the minimum we got achieved. There's just no way at all in knowing how so this is our xk, how small the function value may be just over here, because it may just go down infinitely fast, more or less. So, but with the Lipschitz continuity, we have a bound on the slope. We know that if we have here this function value in the neighborhood of a certain size, the function value can only decrease a certain amount. Yeah, with a thicker pen I tried. I can try. But then I can't erase anymore. I tried. Okay. So this is the class, and the next one is the oracle. This is what it's called sometimes. And the oracle shall tell us what are we allowed to do, what information of the function are we allowed to use in each step. And this should be like this. In each step, get one function value. F of x at some point x and q. So we don't allow anything more than that, because, well, what could we do? So we don't have derivatives available. Our function is just Lipschitz continuous. There's no derivatives, no subgradients, nothing. We can use function values. And so we keep all the value, all the x's we queried, and all the function values. We can use all of this to construct some of our next guess where we want to look at the function again. Okay, so now here's one algorithm which tries to solve a problem of this class and only uses this. And this is a very simple algorithm. I think it's called algorithm 1 in the lecture notes. It's called grid search. Yeah, and it works like this. The input is some natural number p, and then the step it goes like for all pairs of indices like I1 to IN, and these should each of this should be a number between 0 and p. So which means I1 can be the number 0, 1, 2 up to p, I2 can be the same, and so on and so on. Assemble all the points. The points x, and the x's are indices for all these n indices, I1 to IN, and these should be the vector I1 over p up to IN over p. So, okay. So this, where are these points? Yeah, the method is called grid search, and actually this forms a grid, right? This is our yeah. XL. Okay. So this comes from my this here. Probably this was a k, sorry, which meant at some iterate k, at the kth step of the algorithm. Is there anything else which could be an XL? I hope not. I hope this is your question. So this is called grid search. Well, all these points, they lie on a grid. So this is here 1 over p, 2 over p, and 1 equals to p over p. And so these are all the points which lie on the grid. What the method now does is, for all such x, evaluate f of x. So we just look at the function, at the objective function at all the grid points, check out all the function values, and then check the values and pick x hat such that f of x hat is smallest. So, and then the output would be this pair x hat f of x hat. So this is the algorithm, the grid search algorithm. Very, very simple. Okay, so now we would like to know something about the performance of the method. So how good is it? So what can we achieve with this method? How good of an approximation of the minimum do we get? So and here's the result. I formulated it as a theorem. It's called 17.1 because in the other lecture we are in lecture 17. This is called kind of an upper complexity bound of grid search. For grid search. So an upper bound means we need at least so many iterations to be so good. You mean this one here? So this x here, yeah. So that's just how the method goes. So this is just what I this is just as a motivation, or as a simple method which is simple to analyze. We just consider the x's here on this grid. So maybe a short spoiler here. We will show that this grid search is pretty bad. It's kind of slow and it's not very good, not very efficient in the way that the solutions it produces are not very good. But later on we will show that no algorithm can be much better than that. Okay. Okay. So upper complexity bound. So let's denote with f star the minimum value, which we would like to compute with our method. X hat output of grid search. And then we have that the difference, so this the value we got and the value we would like to have, this is smaller or equal to L divided by 2p. So if we make the effort and check all the points of this grid, then we are guaranteed, if we pick the x hat with the smallest function value here, we are guaranteed that the distance to the minimum possible value is not larger than Lipschitz constant over 2 times p. Okay, we will see that this is this is not very good. So, and the proof now is not so difficult. Yeah, so it's not so difficult. So first, let's say that that the minimum value is assumed is attained at some x star. So once again, here is our Q, and somewhere here is our x star, and this is where the minimum value is. So then this x star is part of one grid cell. So I just put, so here's one of the grid cells. Okay, so I hope I already answered the question that this choice of grid is not particularly important, but this is easier to analyze. So let's say this is our grid cell, and the point down left here, I call that X, and the point up here, I call Y. And then so this X star, the algorithm has never seen. The algorithm can only check the points on the grid. So, and now we just choose which is the largest, the closest point on the grid to X star. So we just say let's let, I think what to call it, X bar. Let X bar be the closest point to X star on the grid. In the lecture notes, I've written down formula for these. In this case, so they can be obtained. So you just divide this cell here in half, like that, and then you'll see that this one here, in this case, it would be this, would be the closest one of the corners. Would it be the grid bounds? You mean one part of our problem statement was that we're minimizing over Q, and Q was the unit cube. So we just, by definition of our problem, have that this is 1 and this is also 1. So this is just the unit square here, and then the n dimension would be the n-dimensional unit cube. And we just chose the grid equidistant, which means from one to the next is always the same distance, but again only for to make the analysis simpler. Okay. So we choose X bar. So this one is our X bar here in the lower left corner. In this example, could be any of the 4 corners. And then what one can see is, because the grid cells have side length 1 over p, is that the distance between the optimal X star and the one which our algorithm can produce, this X bar, is less than 1 over 2p. Well, because this is one of the corners. So the side length here is 1 over p, this is 1 over p, and by moving to one of the corners, we don't have to move more than half the side length in each of the coordinates. Okay, and so what gives us, this gives us that, now by Lipschitz continuity, we have that this f of x bar minus f star, that's actually it's the same as f of x bar minus f of x star, and this is then now we can also use absolute values here because this is already smaller than that, and then we can bound above from above by Lipschitz. This is the claim of our of the result. So then it holds that. Maybe I should write. Then it holds. And here by Lipschitz continuity, we know that this is smaller than L over x bar minus x star infinity norm, which is bounded by 1 over 2p. So this is now L over 2p. And this is what we wanted to show, and the proof is done. So that's actually pretty fast. The only thing which we need to observe is that for one of the optimal points which exists, there is one point of the grid which is not farther away than 1 over 2p. And then by Lipschitz continuity we have that. Okay, so but what does that mean now? What does it tell us about how good is the algorithm? Yeah, unfortunately it says that the algorithm is not very good. So put differently, so maybe next page here. Put differently, if our aim would be that f of some x minus the optimal one is smaller or equal some given epsilon, so some given number, some given tolerance. So distance, some given distance to optimality. What our result tells us that we would need that you have to choose p in a way such that L over 2p is smaller than epsilon. So this is what we need for our algorithm. We would need that L over 2p is smaller than epsilon, and this is the same as saying that p is larger than epsilon over 2 L over 2 epsilon. Okay, what does this say for the number of grid points? How many points do we have to check before if we have a p such like this? Yeah, let's look at our grid again. In each direction we have p plus 1 points. So in this example we have p plus 1 times p plus 1 because we're in 2 dimensions. In general we have p plus 1 to the capital N, not capital N, sorry, to the small n. This is the number of grid points we have to check, and I wanted to call that capital N. So p plus 1 to the n, this is the dimension of the search space. This is the p which we need to choose like this. And so plugging this in, we get that the number of points which we need to examine is larger or equal to L over 2 epsilon plus 1 to the n. And this is huge. That's a very large number. So if you want to, depending on L of course, but you see if you want to make epsilon just kind of half as small, you need much more points to get just half the accuracy. So this goes very quickly when epsilon goes to 0. It goes like it goes to infinity, like 1 over epsilon to the n, which is very fast. So maybe the take-home message is grid search is not so good. Okay, but is there any better method? This was now one way to analyze the problem. We had fixed our problem class, and we have come up with an algorithm which is able to produce solution of accuracy epsilon with this number of calls to our oracle. Oh, which one? Okay. So that one here. So this is the take-home message here. If you want to guarantee that grid search produces a solution which fulfills this tolerance here, we would need this many evaluations of the function value. Okay, but now the question is, what is the best thing, the best algorithm which we could come up which can solve any problem in the class? And this is now a much more difficult question. So here we have given an algorithm and analyzed how good this is, but now we ask for what is what could the best possible algorithm achieve over all problems of the class. And so there's also an answer to that. And let me first write down the result. It's also formulated as a theorem. It's kind of a lower complexity bound. So if our accuracy is smaller than L over 2, this is not very important, then there is no method that solves every problem in our class actually what we did in the proof was considering the n-dimensional case anyway, right? So here from the beginning we always worked with n dimensions, and this is also everything happens in n dimensions. The only thing which was 2-dimensional was my picture. Everything what I did works in n dimensions actually. This also works in n dimensions. You have to just consider this situation here in all of the n dimensions. So the proof works from the beginning in n dimensions. You just don't see it here because n doesn't appear in the statement. The n only enters when I calculate the number of grid points here. And as you said, right, correctly in the picture, the number of grid points is p plus 1 to the 2, and here it's p plus 1 to the n. Okay, with less than let's say L over 2 epsilon to the n function evaluations or so. So, and from this statement, it's probably not the importance is the exact numbers here, but it says you that it's a statement, no matter how you cook up a method, there will always be one problem where you need at least this much iterations or function evaluations to get a solution which is this good. So let that sink in. So no matter how you design an algorithm for this problem class, only doing function evaluations and nothing else, there will always be at least one problem where you need this many function evaluations to find a point which fulfills this approximation property. Okay. So how can one, so and now the question is not really so why is this important? So then it is important because it tells us without knowing anything more about our problem, grid searches it's already pretty nice. Uniformly over all problems. Even though it's bad, there's nothing which can really do better on all problems. So, and what is also, this is actually 17.2. What is also a little bit interesting here is the idea of the proof. So the steps are technical, but the idea of the proof is not so hard. So the idea of the proof is you consider, so you start with a given algorithm, which could be anything, which just fulfills our assumptions here. And then you try to construct an objective function in the class such that this particular algorithm fails. I call this here annoying functions. We would find, so for a given algorithm, we would find a function which annoys this particular algorithm as much as possible. Okay, so what we do is, we set P as L over 2 epsilon, and these brackets here mean we had, round it down. So this is then a natural number. And larger equal 1 actually because we assumed epsilon is smaller than L over 2 anyway. So we set this to our P and assume that our method, that there is a method such that needs n capital N less than p to the n steps. Okay, we assume that there is such measure, and now we construct a function which annoys this particular method. Okay, now the idea is to build an annoying f such that f of x equals 0 for all examined points. So wherever our algorithm has looked, it always finds f of x for all the x the algorithm has looked at. We always see f of x equals 0, but f star as small as possible. Okay, how can we do that? Okay, so again, I draw a two-dimensional picture. So for n equals 2, and then we just have a lot of query points here. These are all the points which our method has tried. But we still can find a small cube, q prime, inside of q, theorem. So do you mean 17.2 or 17.1? So I will go over this when I finish the proof. Okay. So because there are only at most capital N points in here, and capital N is smaller than p to the n, there is still a cube Qn with side length 1 over p. That does not contain any of the evaluation points. That contains no examined points. So here, inside this, there's still a cube q prime. The side length is p, and there's no examined point inside this p. So right here in the middle somewhere there is our x star. So this is the room we have where we can make our function as small as possible. So what we now do is we set f of x. So our algorithm is already fixed, and now we give the objective function, and it can be written concisely as the minimum of either 0 or L times x minus x star in the infinity norm minus epsilon, or epsilon prime, sorry, with epsilon prime has to be larger than epsilon but still smaller than L over 2. So this looks complicated, but kind of if you look at this from the side, what this does is, so this is our q prime looked from the side, and our x star is somewhere here in the middle. Okay, then this f here basically looks like being 0 here and 0 there, and then somehow it goes down with slope L here to that point. Okay, so this is how the f looks like in 1 dimension. In 2 dimension you can imagine how it would look there. And then this f is L Lipschitz by construction. The minimum of f is f of x star, then this is 0 and this is actually minus epsilon prime, and this is smaller than epsilon, and hence f of x minus f of x star is still larger than epsilon for all, so it's smaller than minus epsilon for all examined x. Okay, so once again, so theorem 17.2. I try to, okay, let's start from the beginning over here. So what the theorem says, if we fix an accuracy, which is our goal for our algorithm, to find an x which is epsilon close to the minimum value, then there is no method whatsoever that can solve or find minima of for all problems in our class which uses less than this function evaluations. Okay, that is the statement of the proof, which means something like, how hard is our problem class? And our problem class is so hard that we need at least L over 2 epsilon to the n function evaluations to be sure that for a given problem in this class we have found a point which is epsilon good. So the idea is basically, it's a bit technical, but the idea is first to make sure that no matter how the points are here in the volume in our search space, there is still a small cube inside which has side length 1 over p, and this 1 over p comes from this value here. So no matter how you pack this number of points here in a cube of side length 1 with in n dimensions, then there's still one of these cube prime inside the larger cube. And once you have that, you can cook up your function such that it's 0 basically everywhere outside of the red cube here, and then in the red cube it goes down as much as possible as it can in the limited space it still has. And so then this is how it looks from the side, and actually this minimum value here is minus epsilon, and the slope here is L. So slope L, and this here then is minimum epsilon. And if you choose epsilon like that, you guarantee that you kind of reach 0 before you come to the corner of the end of the cube. Okay, so probably the technicalities of the proof are not too important, but the overall idea is that you consider first an algorithm is given, and now we try to construct the worst function for this algorithm. So the function such that the algorithm fails most badly for this particular algorithm. Okay, so and takeaway here is that for this simple global optimization problem of bounded Lipschitz continuous functions on a cube, the simple algorithm grid search is bad, but you can't do much better. Okay, so because what you see is a difference here. We've seen that grid search gives an epsilon output with this many iterations, but you can't get better than that. And they're already pretty close. The only difference is this +1 down here. So the difference is still large, but it's a constant factor somehow. So the best algorithm is not much, the lower bound for the best algorithm is not much better than what grid search is able to achieve. Okay, so this problem was not, I did not treat this problem here because it's of great importance, but because in this problem you can make the idea most clear. So what are the important problems which we would like to analyze in the next lectures? So the important problems are different classes. So, and we consider 3 different classes. So classes we consider. So the first one is convex and Lipschitz. So convex and Lipschitz. What's our problem? Looks like this. So that's the first. And now convexity comes into play. We have f goes from Rn to the extended real numbers. Proper, which means it assumes some finite value. It's convex. And also L-Lipschitz. In this case, with respect to the 2 norm button doesn't make much of a difference. And the problem is then minimize f of x over x in Rn, as before. It's always the same thing. So this is the problem class. So we assume that we know that the function is also convex, not only S-Lipschitz, but also convex. L-Lipschitz, but also convex. So our oracle, what are we allowed to do? At a given point, xk, we get one subgradient. Pk, sorry, I also use upper indices for vectors. Pk being a subgradient of f at xk. So we don't even get to know the full subgradient, but only one of them. So our algorithm just gives us one and we can choose. So what does our method do? We want to be fairly general, so our assumption is we have our function, we pick an initial point x0 somewhere, just as we like, and at this point x0 we get a value for p0, a subgradient. And then where would we like to find our next point? And so the idea of the method is the iterates fulfill that, write it slightly different than the lecture note, that the next point, xk plus 1, is contained in the initial point plus the span of all the previous subgradients. So p0, p1, pk. In other words, in case you're not familiar with the span, it says that the is equal to x0 plus, say, alpha 0 p0 plus alpha 1 p1 plus alpha k pk for some alpha I. So in other words, we are only allowed to move in the directions of the subgradients we have already seen. So if we are here, this is our x0, and this is where our subgradient points to, we are only allowed to search on this line. So probably we would end up over here, because this is what, for some reason, we find this is the best thing. Then the subgradient may point here, and then we are allowed to move in this and that direction simultaneously, so we may explore two-dimensional search space over here in the next iteration. So this is our assumption on the first class. Convex and Lipschitz, we start with some point, we get a subgradient, we can move into the direction of the subgradient or in the previous subgradients, end up at a new point, query a new subgradient, and then in this way we're going to explore the space. Okay, that's the first class, and we're going to analyze this in the beginning of the next lecture. Okay, so probably that's now the point for a short break. I always have short breaks in the middle of the lectures here. It's about 2 minutes, so you can do just relax a little bit, look out of the window, drink something, and there was just some music and a few stupid dad jokes here, and then so lecture continues in basically more or less than 2 minutes. So see you then. Okay, so here we're back. So this is the paradigm which is actually used by algorithms, right? So if you do convex optimization, that's kind of a standard procedure. You work with the subgradients which you get. Because why is this a good idea anyway? If this here is some given point xk, and let's say this here is the subgradient pk, then you know that the function is kind of smaller over here than over there, roughly speaking. Which means that the minimum is supposed to be on this side of the hyperplane. So moving in this direction seems to be a good idea. As we'll see, or probably as I don't know if you've seen it already, it's not clear that in this direction always lies a better point, but actually what is true that on this side of the half plane there is a better point, which gives a smaller function value. Maybe not necessarily in this direction, could be like here or there, but anyway, moving here moves you into the right direction of to the right half plane. Okay. So this is the first class which we would really like to consider, and the second class is very, very similar. The second class is convex and lsmooth. Oops, off screen. Convex and lsmooth. So what does that mean? It changes two things. So it changes the problem that our f now is a map from Rn to R, not extended real numbers anymore, so we only say finite. It's convex and differentiable with and now also Lipschitz, but we say that with L Lipschitz gradient. And that means that if you consider the gradient of f at one point and the gradient of f at a different point, then these are two Rn vectors, and their distance should not be larger than L times the distance between x and y. So that is this is what we call lsmooth, differentiable and L Lipschitz gradient. And of course, what you want to solve is minimize f of x over all x in Rn. This is as before. So the only thing more we have is differentiability and an estimate about how fast the gradient can change if we move the point around. So this changes a little bit what our oracle can give us. The oracle can give us at a given point, so this problem, oracle xk, we get some gradient, the gradient, and we call it gk, and this is just the gradient of f at xk. So it's not much different. The difference is now that we have a single valued gradient here. And the method is basically the same. It's again that the k plus 1, so the next iterate is again in this space, which in the search space, which is of the form x0 plus the span of all the gradients we have seen. So the same as before, we are at some point. We know the gradient goes in the direction of the gradient it goes up, and we go probably in the opposite direction or something else because we already know something more about the function. At the next point we get the next gradient, and then we know in another direction which may be worth to explore, and so on. We move always in the direction of the gradients we have already seen. Okay, that's the second problem class, and now comes the third class. It's lsmooth and mu strongly convex. wrong color. This should have been blue actually, right? This should be a blue line here. And this is here totally the same as before. Same as convex and L smooth. But F also mu strongly convex. But all the rest is the same. So we have also the Lipschitz bound. We also want to minimize F. At each iteration we only get one gradient and nothing else. And we only can move in the span in this search space over here. Okay, and so what we're going to see, again a spoiler, is that the first problem, the convex and Lipschitz, this is still hard, but it's much simpler than without convexity. It's much simpler. This problem is even easier, and this is even easier. And we're going to see this in kind of two different ways. So first we're going to see that there is an algorithm which is able to solve this kind of problem with given complexity. So say we need this many iterations to get an accuracy of that epsilon. So I don't know. Yeah. And this gets better and better the smaller the class gets. But then we will also see a lower bound on the complexity. There's no algorithm which can do better like that. And then our goal will be to construct an algorithm which kind of matches the lower bound, which is then called an optimal algorithm for the class of problems. This will be not totally possible. We cannot match the lower bound perfectly, but we can match it up to constants. This may become clearer in the next lectures. Okay, so before we can analyze these class of problems, we need some more properties of the functions in these classes here. Okay, so we've already gone over a few properties of convex and Lipschitz continuous or convex and L smooth functions, but we need some more inequalities, and these are going to be stated in the next theorem. This is now a list of properties for L smooth functions. Theorem 17.3. The following is equivalent. The following conditions are equivalent. So each of them conditions are equivalent to F being convex and L smooth. Okay, the first one is we have 0 smaller equal than f of y minus f of x minus gradient f of x y minus x plus, and this is smaller equal than L over 2 x minus y squared. So if this holds for all x and y, then the function is convex and L smooth, and vice versa. What is also equivalent is that for all x and y, f of x, plus gradient f of x times y minus x plus 1 over 2L times the norm difference of gradient of f of x and gradient of f of y squared is smaller than f of y. So you may notice that some of them looks pretty similar, but actually it's different. So this quantity f of y minus f of x minus this in the product can be seen if you bring this to the other side. Then you see that this quantity is also bounded from below by that, and that also characterizes convexity and L smoothness. The third property is that for all x and y it holds at 1 over L times the gradient difference is a lower bound for the inner product of the gradient difference minus the point difference. And this is equivalent to all of the above. The fourth thing which is equivalent to all of the above is an upper bound for that term. L times x minus y squared. The fifth one is that for lambda in between 0 and 1, it holds that lambda f of x plus 1 minus lambda f of y is larger equal f of x plus 1 minus lambda y. And then we have here another term plus lambda times 1 minus lambda over 2, the gradient difference. There's an it's over 2L x gradient f of y. So that's kind of a strengthening of standard convexity, of Jensen's inequality for convexity. You have an additional term on the right hand side which depends on the gradient difference and with 1 over L. And the sixth condition is that lambda f of x, and again lambda between 0 and 1, 1 minus plus 1 minus lambda f of y is smaller equal f of lambda x plus 1 minus lambda y, and here we have plus lambda 1 minus lambda times L over 2, and here it's x minus y. Okay, so it's a long list of equivalent conditions. And so the way we're going to use it is mostly, if we have a convex and L-smooth function, we can use one of these inequalities. The other implications are also interesting, but we're not going to need it, that if a function looks like this, or actually we're going to need it in theoretical, we're going to also want to need these. Okay, let's see. So what's our REST program? We want to prove this, and then there's at least 3 more theorems I would like to give. So probably I'll go like this. I first state all the results we have for today, and then see how much time is left to formulate the proofs. Complete proofs are in the lecture notes anyway, so I think it's more important for the lecture here to go through the statements. Oops, what happened here? Yeah, that's tough. So maybe I try it for a few of them, but I can't do it for all of them because for some I don't have a good picture. So maybe this one here is that's the one where I can draw a nice picture, the first one. So, okay, convex functions, I always picture them like that, even though they may have a kink. But no, they are L-smooth, they can't have kinks anymore. So what this says is, probably I write it differently. I write it like, so I add f of x plus gradient f of x, y minus x to everything, so then they get this one. Yeah, it's plus. Oops, off screen. Here, everything is everything. So now we consider x fixed to be some point here, and y is now the variable. So the thing in the middle here, that's the black curve. That's f of y. Okay. What is the thing on the left-hand side here? The blue thing. The blue thing is the linearization of the black function at the point x. So it's f of x plus a linear function, and this is the slope, so this is this function. And so the lower inequality says that the function is below, above its linearization. So what is the right-hand side? So the right-hand side lies above the function. This is what the upper inequality here says. And this is the linearization plus this quadratic term. That's the quadratic term which is 0 at the point x. So the upper and lower points are exact at this point here. And this kind of deviates from the lower estimate by a quadratic. Something like this. And so what you can see from the picture is the size of L, but so the smoother L, the smoother the function, which means the smaller the L, the closer this red line moves to the blue line. And so the more the function itself is squeezed in between a linear lower bound and a quadratic upper bound. That's probably the most important thing here. That one is also interesting because it says that you also can squeeze something not linear below the graph. You see, this is here, that's again the black one here. And the left side here, I could try to paint it green, and but anyway, it's something which is larger than the blue line here because it adds this term, but it's not purely a quadratic function because it's kind of non-quadratic here because there's the gradient involved. But it's a nonlinear function which still fits in between the blue and the black. So this I just do it here. This is about green. This one is below the black and it's larger than the blue. So it's somewhere here, but I have really not a good idea as to how it looks because it depends on the gradients at all the points. So, but you get something larger than the blue and nonlinear between the blue and the black. And these things here, I don't know how to visualize this. One thing I wanted to add is that the property 3, is it 3? Hey, let me check, yeah. This one here, so a lower bound in the distance of the derivatives. This property is sometimes called co-coercivity. Coercivity. So it's not related to coconuts, but for some reason coercivity is a word, so in co-coercivity is kind of a dual word, but I don't like this naming, but this is how it's called. This is called co-coercivity of the gradient map. Okay, we will need it in the later part of the lecture, but I think in lecture 23 or something, where this short course here is done already. Okay, this is the illustration of the parts of this theorem that I can illustrate. Okay, good. Here we go. So, yeah, we can use this here again. For the next thing. So the next statement is lemma 17.4. For some reason this guy here jumps. This keeps jumping back to that. Okay. Okay, lemma 74. If f is differentiable and mu strongly convex, convex if and only if, so exactly if for all x and y we have that f of y is larger or equal f of x plus the linearization, and then here's plus mu over 2 x minus y. Okay, so this looks similar to the green bound here. It looks similar to that, but note the difference. It's again f larger than the linearization, but the last term differs. Here is the difference of the points, and there it's the difference of the gradients. So this one here, the right hand side, is exactly a quadratic function in y. So this is a constant, that's a linear, that's a quadratic, this is a quadratic function in y. And this here is not, because it's not quadratic because of the gradient here. So I could draw the same picture here, but then I would say that the green line corresponds to this right hand side here, but it's a quadratic. And when I drew the green line for that, it wasn't a quadratic, it was something else, but it was in between blue and black. It's still between blue and black because it's larger than linear, because this is positive here, and it's smaller than y by the lemma. So and then you see if a function is mu strongly convex and L smooth, then the graph is always bounded between two quadratics, one quadratic with kind of constant L from above, and another quadratic with constant mu from below. So that's very important for the last class of problems, which is strongly convex and L-smooth. They are always bounded, squeezed in between two quadratics. And by the way, you always see, because these two inequalities both hold, the lower bound here and the upper bound there, the L has to always be larger than the mu, which I find quite amazing, because it doesn't look like it. It's kind of, strong convexity and smoothness doesn't seem related, but you see that if a function is L smooth, it can't be more strongly convex than being L strongly convex. And if it is, the function, the upper and the lower bound match, and the function looks exactly like this. Okay. So that is one of the next lemmas. So the next one is again, I could probably have joined it with this one, but for some reason I just, and also I call it theorem, probably it's not that well organized. So 17.5 is, because it's not an if and only if, f mu strongly convex, then, and I only prove then. The first thing is we also have an upper bound here, which is f of y is smaller or equal to f of x plus linearization. And then here I also have plus, now it's 1 over 2 mu, and here's the difference of the gradients. So it's an upper bound here, and it's again, this could be the red line, only it's not a quadratic function because it's here, it's the difference of the gradient and the difference of the points. So you can consider it a little bit like that, but it's still a little bit different. So that's one thing, and another thing is you also have that the gradient of f at x minus gradient of f at y times x minus y, and then the product is bounded from above by 1 over mu times the difference in the norms of the gradient. So, and if you can't memorize all these things, I guess you're in good company. So at least it's the same for me. I always have to look them up. So I kind of remember this picture here. I always know that this is true, and usually I also know that this is true here, this upper red bound here. But when it comes to this, I'm always look it up, actually, to be honest. And the same holds with all the things here in lemma 17.3. I tend to always look them up, although it would be much better if I could know them by heart, but unfortunately I still struggle with that. So these are also important things we would need to, we're going to use in the next lectures when you analyze methods and problem classes for convex optimization. And the last result which we're going to need is now something for the case when the function is strongly convex and L-smooth. So theorem 17.6 is f is mu strongly convex and L-smooth. Then we know that f is larger than mu. We know that already from the previous, and for all x and y, it holds that that we can bound the difference of the gradients times the difference of the points from below by something which now combines L and mu in a clever way. It's mu times L over mu plus L times x plus y squared and plus 1 over mu plus L difference of the gradients squared. Yeah, one more inequality. I'm sorry, there's a lot of inequalities. Yeah, so and so this really is a combination of something related to 17.4 and 17.3. So in 17.3 we had this lower bound, the co-coercivity here, this inner product, the same as here, is bounded from below only by a term like that, 1 over L. Now, right. I'll tell that later on. Correct. So you only have this term here, but you can get an additional term. Also, you can squeeze in a little bit of x plus y squared, which is kind of related to what is here. Actually, I could have done that also. This expression here, because it holds for all x and y, it's also equivalent to saying that this term here has a lower bound like that, but only with the coefficient of mu. Mu over 2, I guess. So in this now, if you have both of them, you kind of get it mixed, and you can have a little bit of this and a little bit of that. And you are right. It has something to do with the condition number, exactly. So what is called condition number of a convex optimization problem is often just L over mu, L divided by mu. Maybe I would introduce it in the next lecture, but since you mentioned it now, why not? So in this case, the condition number is often called Q, at least I do it in this lecture here. It's L divided by mu. And you see, because of L being larger than mu, this is always larger or equal to 1. And the smaller it is, the closer it is to 1, the more does the function look like a nice quadratic function. And you probably know that minimizing quadratics is the simplest case. For this you have methods like the conjugate gradient method or direct solves or whatever. So, but the larger the condition number gets, kind of the harder the problem is to solve. But that's not the full story, because we will only also consider the case mu equal to 0. This was our first two function classes did not have any strong convexity built in. So we'll also have the case mu equal to 0 and still get some meaningful stuff in there. Okay, we still have 15 minutes. So I can prove some things here. I don't know which one would be the nicest. I don't know. So probably, I don't know. Does anybody have a preference which one I should prove? These are the three last, and then there's the long list. Then theorem 17.3. I don't know. Maybe if you write something, I can do that. Otherwise, I will pick one. So probably I do the last one, because I find that the 17.6. Actually, we're going to use the previous ones because, yeah, but maybe I do the last one. Let's prove the last one. Because it's the most involved, but the proof is actually not so hard. So what we do here, namely, is we set we define a function phi of x as f of x minus mu over 2x squared. And then one important property is, if f is mu strongly convex, it stays convex if we subtract mu over 2x squared. So still convex, since f is mu strongly convex. So we have also that the gradient of phi, oh yeah, probably that, oh yeah, sure, right, thank you. So this was totally wrong, you're totally right, this should be a minus sign here, correct. I hope it's correct in the lecture notes, yes. Yes, we have to. So the gradient of this function here is then, just by calculus, the gradient of f minus mu times x. And this shows, also using previous results, that this phi is L minus mu smooth. So it kind of subtracting mu over 2 times norm x squared reduces the constant of strong convexity by mu, so we still have convexity, nothing more, but it also reduces the smoothness, and this can be seen by that. This is L Lipschitz, and if I subtract this, it's at least L minus mu Lipschitz. Okay. So then we have one first special case. If L is equal mu, then we see, and actually this is theorem 17.3.3 and theorem 17.5, that f of x actually has to be equal to mu over 2x squared, because it's squeezed in between two quadratics, but these quadratics are the same, so the function has to be the quadratic itself. And then you can just check this, that it's true. Then it's so. Then the function looks like this. So this is just mu times x minus mu times y, and everything checks out. I would say check inequality by hand, so by direct calculation. Yeah. Okay, that's the boring case. And the more interesting case is the case mu is actually smaller than L. Then what we do is, let's probably still keep the function phi in here. We apply theorem 17.3, the third point, to phi, because we know that phi is L minus mu smooth, so probably I should put parentheses here, L minus mu smooth. And then this gives us that the gradient of phi of x minus gradient of phi of y times x minus y is larger or equal. Let's check what that was. It was that here. Oops, it was that. This one here. Bounded from below, difference of the gradient squared times 1 over L. But in this case, L is L minus mu. So we have here 1 over L minus mu times the difference of the gradients. Okay, now let's evaluate everything. So let's keep in mind that we have this here. So this here is by the blue equality up there. This gives us a gradient of f of x minus mu x minus gradient f of y plus mu y, x minus y, and this is nothing else but gradient of f of x minus gradient of f of y, x minus y, minus mu times norm x minus y squared. These x and y combined with these to 1 norm squared. And for the right hand side, we probably do the same thing. We also use the blue inequality here, and then I don't have enough space over here, so I just write it down there. It's 1 over L minus mu times norm of, and then I just clean up a little bit. I clean it up like norm of f, gradient f of x minus gradient f of y minus mu times x minus y norm squared. And what I now do is I expand the square. I expand it as that. Expanding the square gives us gradient of f of x minus gradient of f of y squared minus 2 times mu inner product of gradient of f minus x x minus gradient of f of y, x minus y, and then still plus mu squared from the last one, norm x minus y squared. Okay, so we have that the left hand side is this and the right hand side is this. So what we do now is we say these two things, this one is larger than that one, and you just write it side by side and clean up. That's what one needs to do right now. That's the full proof. Okay. So, and I think the lecture notes just say plugging these two things in and comparing this and cleaning up proves the result. And I think it's basically technical. Should I try? I think if I try, I'm gonna make mistakes. But yeah. So what we do, let's just see if everything checks out. So on the left-hand side, we have gradient f of x minus gradient f of y times x minus y minus mu x minus y norm squared. And this we know now is larger or equal to 1 over L minus mu norm f of x minus norm f of y squared minus 2 mu over L minus mu inner product and plus mu square over L minus mu times x minus y norm squared. Oops, I'm off screen here. So this is just everything we had on the previous paper, now combined. Okay, so and what is what we wanted to prove? We wanted to prove some inequality where we just have this on the left hand side. So what we do is we bring this to the left hand side, this to the right hand side, and then we divide by the coefficient of this, what we get on the left hand side, and see if we get that here. So we take this and bring it to the left, we take that and bring it to the right. So what do we get? We get here 1 plus 2 mu over L minus mu times the gradient difference. And this is larger or equal to, well, that one is already nice. It's not as it should be, but it's close. And then it's plus, and now this looks a little bit weird. It's mu squared over L minus mu times x minus y squared. So that should be it. We only need to divide by this. Okay, let's calculate what this term is here. This here is actually, if we bring it to the common denominator, L minus mu, and then we get L minus mu plus 2 mu, which is actually L plus mu divided by L minus mu. Okay, so what we do now is to take this inequality and multiply by the inverse of that. So what we get here, this follows from that, and from that it follows that, in a product of gradient f of x minus gradient f of y, x minus y, larger or equal to. So this now is simple. We multiply by the inverse of that. So by L minus mu divided by L plus mu. If you multiply by this, we get 1 over L plus mu as desired. And what is left over here? This looks now complicated, but it's not that much complicated. This gives us, so we divide by the inverse of that. It gives us mu squared divided by L plus mu. I do. Minus the reciprocal of that, and then mu times L minus mu divided by L plus mu, so we can just write it like this. So, and it remains to check that what is up here is actually nothing else than mu squared there's some yeah, I made one mistake. I made one mistake when I brought this term to the right hand side. I should have written a plus here because it has been there with a minus sign, so it's a plus here, and so we also have a plus there, and then it makes sense. So this is now then mu squared plus mu L minus mu squared. Actually it's mu L, and that's what should be there. Okay, question, can you please go over the proof again? Yeah, I can do. So we're close to the end, and let's try to check if we take the proof again. So, what's the statement here? The statement was, if our function f is mu strongly convex and L smooth, then it fulfills this inequality with these two terms on the right hand side. So the idea of the proof is to use the fact that it's mu strongly convex to subtract mu over 2 times x squared from f and still get a convex function. That's one of the basic properties of strong convexity. That's one of the definitions you can use. If you subtract mu over 2 times x squared and it's still convex, then it's mu strongly convex. Then a simple calculation shows you that the gradient is just the gradient of f minus mu times x. And from this you deduce that this function phi is actually L minus mu smooth. You can do this, for example, by using one of these characterizations here. Probably this one is the simplest. Or that one, I think that one is the simplest. So then by subtracting mu over 2 times norm x squared, you kind of lower the constant of strong convexity by mu, but you also reduce the constant of smoothness also by mu. And then the case L equals mu is probably not so simple or not so interesting. Then you apply one of the results of the previous things on L smooth functions to the function phi. And this says that for the function phi, it holds that gradient difference times point difference bounded from below by 1 over the constant of smoothness times gradient difference. So that is now just this statement here applied to phi with this reduced smoothness here. And now you plug everything in and clean up. So the rest is kind of mechanic. You plug the gradient of phi in, you get this term, you formulate to this. And so you also plug the gradient of phi, you get this long quadratic, you expand the quadratic to this, and if you have now this is larger than that, you clean everything up. And the cleaning up takes another page actually, but everything checks out. Okay, so that was a little bit more than I expected. Let's see how we can do in the next lecture. So I would like to cover the same things which I planned, but then let's see if we can still keep to the schedule. So so the lecture had basically 2 parts. So the time is over, but in case you have 3 more minutes, I will go over the 2 different parts once again, just to put everything in perspective. So the first part the aim was to introduce you to the idea of upper and lower complexity bounds. So in the upper and lower complexity bounds we fix a class of problems like that one here, and then first we try to find an upper complexity bound by giving an algorithm which gives an approximate solution of desired quality and a guaranteed amount of time measured by queries to our oracle. That was for the grid search. And then lower complexity bounds is results like this, saying if we fix an accuracy, then there will be no method which can solve every problem in our class faster than a given number of queries. And the idea to prove such results is to fix the method and then find the worst problem, the most annoying problem for that class. So we could manage in our class of only Lipschitz continuous function on the unit cube that we have an algorithm and a worst case bound which are already just differ by some by some constant here. So they differ by a constant factor, which means they have kind of the same order, like 1 over epsilon to the n. This is how the number of iterations goes up. So, and after we did that, we introduced the problem classes, which we're going to analyze in the next lectures. In the first lecture, we talk about convex and L-Lipschitz functions. And we will show that the subgradient method is actually the best you can do in some sense. Then we will consider 2 more classes, convex and L-smooth, and convex, L-smooth, and also strongly convex. And there we will see that the gradient method is not optimal. We have a lower complexity bound, which is in order better than what the gradient method can achieve. So the gradient method, we will talk about this, is a straightforward method, but you can apply to these, and you can show that it's off. It's not matching the lower complexity bound. And then the great miracle is one of the kind of really great achievements from the last century in the 80s by Nesterov and Nemirovsky, devising a simple algorithm which matches the lower complexity bound, which is in some sense the best algorithm for this class of functions. Up to a constant, but only up to a constant. So, and after we introduced this, we just had the collection of all these long statements, a lot of inequalities characterizing convexity and L-smoothness, some more inequalities for mu strongly convex functions, and then one final inequality which holds for functions which are both strongly convex and L-smooth. Okay, that was probably a lot to digest. I hope we can do it. Tomorrow there will be the next lecture where we analyze the subgradient method and probably also the gradient method, if I recall correctly. And then at the end of the week we will have 2 exercise classes where you can go over the notions of convexity again together with Lionel. Okay, thanks for listening, and if you have questions, try to keep asking them in chat. Okay, that's it. Thanks for listening.